Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture on control systems. So in the last lecture we wrapped up our discussions on observability, and we saw that, well, if there are two observable realizations, then there always exists a similarity transformation between the two of them. Yeah, so at one go we are sort of compiling a lot of threads together. We also introduced this notion of observability, and apart from that we've shown you that there are certain realizations like the observer canonical form, which is always going to be observable. Yeah. And then we finally saw that between any two observable realizations there exists a similarity transformation. Thereafter we embarked on this journey to understand the dual of this notion of observability, which is controllability. We saw that the observability had everything to do with whether you can infer or you can deduce the information about the states from the output, and then we saw that the notion of controllability has everything to do with whether through some suitable inputs applied at the input channel you can drive the states from any point on the state space to any other point on the state space, right? If it is doable, if it is achievable, then such a system is called controllable, right? We've also taken this toy example of a 3x3 system, a third order differential equation realized in the phase variable canonical form. Of course, I haven't proved in general that the phase variable canonical form is always going to be controllable, but by the analogy with the third order system you might always extend it to the nth order system and then understand that, you know, by taking sum of the impulse and its derivatives suitably scaled, you can get from any state to any other state in virtually zero time, right? So therefore in that sense the phase variable canonical form is always going to be controllable, and we've done all of this without even touching on any of the well known tests of controllability that you might come across in different textbooks, right? Okay, so today we're going to start with the general problem of controllability, not necessarily related to this setting the initial value at those suitable banks of integrators, right? So as you can see before yourself on the screen now, we have this definition of observability, controllability, the rather loose definition of controllability which we ended the previous lecture with. Now today we're going to start with the general formulation of the problem. So suppose you have, we know this to be true, that x at t2 at any instant t2 is given by e to the a t2 minus t1 times x t1 plus integration from t1 to t2 e to the power a t minus tau b u tau d tau. Notice that this is very consistent with the way we understand. Don't get confused by the fact that we have t1 instead of t0 or 0 here in the lower limit of this integral, right? That's because you notice that the definition of the states tells me that if I start my journey from any reference frame, so suppose my reference frame is t1, then I don't care about the way I have reached this particular state. Yeah, if this is my state, yeah, at the instant t1, I don't care about how these n tuples have been arrived at through this u1 or u2 or u3, which one has taken me explicitly here. I don't care about that. All that I care about is the value of the state at t1 and the input that is applied thereafter, t1 to infinity, yeah, in this interval. With the knowledge of this alone, I should be able to cook up the journey of this state vector with respect to time thereafter, yeah. So that is exactly how this notion is consistent. So please make a note that for the purpose of this equation, it is as if this t1 is my initial instant, right? And we've seen that this property of this transition matrix as well, right. So this is of course true of any causal system. So any input that you are applying from so any input that you are applying from this t1 onwards cannot affect the states before the instant t1, yeah. So therefore these are already carved in stone, nothing can be done about them, right, yeah. So because it is causal, this is important that this is true in general, right. Okay, so now having understood this, remember in the previous day's formulation we call this eta and this eta hat. So let us go by that notion. So this is eta hat which belongs to r to the n, this is equal to e to the a t2 e to the a minus, my bad, it's going to be e to the minus a t1. Remember in general e to the power, I had mentioned this earlier but it never hurts to remind, in general e to the power p plus q is not equal to e to the power p times e to the power q, yeah. So if e to the power p plus q is equal to e to the power p times e to the power q, if and only if, again this is a result which we shall not prove, this will take us too far afield into matrix theory, if and only if pq is equal to qp. So if those matrices commute, only then, yeah, only then these can be written in this form. Unlike in the scalar case where the exponential function actually exists, remember in this matrix exponential we have defined it to be the matrix exponential, so nothing is obvious, yeah. You can only write e to the power p plus q, where p and q are matrices, as e to the power p times e to the power q if and only if p and q commute, yeah. And in that case this, whether you write this as e to the power p times e to the power q or whether you write this as e to the power q times e to the power p will cease to matter, they commute anyway. So the p and q commute, e to the power p and e to the power q also commute, okay. So because a commutes with itself and t1 and t2 are just scalars, so I can actually write this as e to the power at2 minus at1, therefore it is e to the power at2 times e to the power minus at1, yeah. So that is important, don't make these mistakes like thinking that this is a general case that holds. You might not make that mistake in this course, because in this course you will always be dealing with the same system matrix, but in general do not go with the notion that this is in general true, it is not for any arbitrary matrices, okay. Anyway, so then we have this x t1 plus, again I am going to pull out this, sorry this is going to be 2 t2, right, yeah, because we are evaluating at t2, so this is going to be e to the a t2 integration from t1 to t2 e to the minus a tau b u tau d tau. Now I am going to do something, I am going to multiply by e to the minus at2 on both sides, yeah. I can always do that because this matrix is always going to be non-singular, no, the matrix exponential, because it is a state transition matrix, as I said in the previous lecture also, it is always going to be non-singular. So therefore what I can do is, I can just write e to the minus at2 eta hat, and I note that this is nothing but eta, right, minus e to the a t1 eta, yeah, where eta hat and eta could be any arbitrary vectors in state space, right, yeah. This is equal to integration from t1 to t2 e to the minus a tau b u tau d tau. Please pay very close attention to this particular equation, it is going to be of pivotal importance to our discussions, right, because this is going to allow us to prove the condition for controllability in general, okay. How so? So let me go to the next slide, just recall. Now notice something here, that this, because my choice of eta hat and eta is arbitrary, this overall thing can also be arbitrary, no. So since eta and eta hat could be arbitrary, yeah, therefore this overall thing v is also arbitrary, right. So if this is arbitrary, as I have called this v, so let this v, which is another n tuple, an arbitrary n tuple of course, yeah, remember T1, T2 are constants now, right. So if T1, T2 are constants, then this is a constant vector, right. Okay, so now this V is going to be nothing but this integration e to the minus a tau b u tau d tau from T1 to T2, alright. Now provided that this is the case, yeah, what can I do? Recall our famous Cayley-Hamilton theorem, yeah, that Cayley-Hamilton theorem allowed us to say that e to the minus a tau is going to be I minus a tau plus a squared tau squared by factorial 2 minus so on and so forth, yeah. Now notice that beyond a to the power n minus 1 tau to the power n minus 1 by factorial n minus 1 and then of course minus 1 to the power n minus 1, beyond this whatever terms come like a to the power n, a to the power n plus 1, all of them can be represented in terms of these fellows, right. So it is the same with a to the power e to the power a tau. Similarly e to the power minus a tau can be written as, yeah, can be written as some alpha 0 I, yeah, again of course let me not miss out on the argument here. So alpha 0 as a function of tau times I plus alpha 1 as a function of tau times a plus alpha 2 as a function of tau times a squared plus dot 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 till you finally have alpha n minus 1 as a function of tau times a to the power n minus 1. That is all there is to it, because all terms beyond a to the power n minus 1, that is from a to the power n onwards by Cayley-Hamilton theorem, can be represented in terms of I, a squared, a cubed, and their linear combinations, right, yeah, okay. So therefore let me replace this here. So then I have this V is going to be nothing but this T1 to T2 alpha 0 I plus alpha 1 a plus dot 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 till alpha n minus 1 a to the n minus 1. Well, if you are a stickler you would sort of grumble now because I have not written the tau as an argument. So let me satisfy you there and sort of not be wishy-washy here, alpha 1 tau a plus dot 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 till alpha n minus 1 tau a to the n minus 1 times b u tau d tau. But what is this? How can I write this? Now notice this is going to be nothing but, what is this first one? So if I pop this, we have done this very similar thing a little while earlier, right, when we are proving this observability result. We used the Cayley-Hamilton theorem, remember, in 1 or 2 lectures back, right. So now let me push this b inside. So what I then have is this T1 to T2 and then I have this alpha 0 tau b plus alpha 1 tau ab plus alpha 2 tau a squared b plus dot 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 till alpha n minus 1 tau a to the n minus 1 b times u tau d tau, yeah. Now you might wonder, is there an efficient way of writing this? Let me block this part out, this might be distracting your vision, yeah. So now you might be wondering, is there an efficient way? Now notice what is this B looking like? In our case it is a seesaw system, so B is a column. AB, A is n cross n, B is n cross 1, so AB is n cross 1. A squared B similarly n cross 1. So these are all column vectors. Notice this is a column vector, this is a column vector, this is a column vector. So this is basically some linear combination of the columns. Of course these way I am combining these linear combinations, these are not constants but functions of tau. Nonetheless this is a linear combination, maybe a time varying combination, right. So therefore the way to write that, yeah, and note that this alpha 0, alpha 1, alpha 2, these are all constants. I mean sorry, not constant, these are all scalars, not vectors themselves, of course not constants, they are functions of tau. So therefore, can I not write this as integration from t1 to t2 b ab dot 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 till a to the n minus 1 b times alpha 0 tau alpha 1 tau dot 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 till alpha n minus 1 tau u tau d tau. And now I better pull this on out. So this is going to be equal to this v that I have defined, yeah. So now I better pull this fellow out. So this is going to be b, this is going to be ab, this is going to be a squared b, yeah, it's going to be a to the n minus 1 b, like this, times this integration of alpha 0 tau u tau alpha 1 tau u tau dot 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 till alpha n minus 1 tau u tau d tau is equal to v from t1 to t2. So let me treat this as unknown. Let me put the unknown in a red box here. Yeah, this integration of this vector, this is the unknown. This, given the system, this is known, right? Because the AB matrices are known. This, given that you have told me that where you want me to go from some place at t1, that is eta, to eta hat, right? So if you have given me the eta and the eta hat, then I can always evaluate e to the power a t1 and e to the power a t2, and therefore I know what my v vector is. Yeah, this is the vector that I have called v, remember? This is the vector that I have called v. Yeah, so this is known to me, this is given to me, this is known to me, this is given to me. So this is my final position where I want to go, that is eta hat. This is my initial position where I was, that is at eta. Yeah, so I was at eta at time t is equal to t1, I want to go to eta hat at time t is equal to t2, right? And then this left hand side, this v is completely determined, right? So this v is also known. But what does this remind you of? Yeah, what does this remind you of? This reminds you of, yeah, this reminds you of the linear system of equations, right? You have some matrix A, not this system matrix A, yeah, you have some matrix A times a vector is equal to some other vector, yeah, and it's a square system, right, because it's a seesaw. So there are exactly, the size of this fellow is n, and there are exactly n columns, so it's an n cross n matrix. So when is this solvable? Yeah, when is this solvable? Of course, one condition is that B, AB, this matrix B, AB dot 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 till a to the n minus 1 B must be of full row rank. Yeah, in this case, of course, because it's a square matrix, row rank is equal to column rank, so therefore, and thereby it implies that it's going to be invertible. So non-singular as well as invertible. Yeah, so if it's full row rank, which means full column rank, yeah, and therefore it's invertible. So this matrix we define this as C. So this is the curly C, not, I wonder if my handwriting makes that distinction to you, but this is not the C matrix as the one which appears in the output, this is the curly C. Like remember the observability, the O I wrote in a curly fashion. So here also this C matrix, this I am going to write in this curly fashion, and this is called the controllability matrix. Yeah, C is the controllability matrix. So C is the controllability matrix, and therefore for controllability, in order for this problem to have a solution, you must have that this is invertible for the seesaw case at least. Yeah, for the MIMO case you need full row rank. Yeah, we will not get there. Again, that is within the ambit of some advanced level courses beyond the scope of what we are going to discuss here. Now you wonder like whether it is possible that I mean it's maybe a necessary condition, but is it sufficient, right? So can I always cook up an input? Now unfortunately here I am not going to be able to give you explicitly what this u is going to be. As I said, evaluating that input explicitly is not a very easy thing to do. So although it is difficult to explicitly tell you what this u should be in order to take you from one state to another, yeah, well for that you actually need ideas about something called the controllability grammarian, which is basically a Wronskian. So never mind if you have never heard of these terms, we will not be delving into that. However, I will give you a quick sketch of some sort of a proof, not really, to convince you at least that there does exist some way to go from one state to another in very little time, okay. So for that let us take this case, right. So suppose now T2 tends to T1, right. So we are saying that, well, if my state has to go from one position to the other in the state space, right, and that time that is granted to me is very small, and if I can still do that, then of course if I am given more time I can do better, in the sense that I can use lower energy control signals or lower energy inputs to possibly get there, right. You understand that if we have to do something in smaller time, we have to expend higher amount of energy in some sense, right. So at least for this case, yeah, can we say that there does exist something? If it does, then in principle we should be able to get a controls when this spacing between T1 and T2 is increased. So let us see how this expression turns out. You know, we use the same old state equation. Of course we then have this e to the a T2 minus T1 times x T1 plus integration from T1 to T2, okay. So we let T2 tend to T1, yeah, and this is well, we know this is e to the power a T2 minus tau b u tau d tau. So we are not going to explicitly prove to you that this solution will always exist, yeah, that will involve some rigor which we are not in a position to employ at this undergraduate level, but at least when T2 and T1 are very close together, there does exist a solution that I will convince you of. Of course the solution may not be to your liking, because as we shall see we will be using these impulses, yeah. So let us see how that is done. So now note that as T2 tends to T1, we can write this equivalently as x of T2 minus x of T1, right. This tends to 0, so a times 0, that is the identity, right. So that is the approximation we will be making, is equal to, now you have this T1 to T2 e to the a T2 minus tau b u tau d tau. Now remember that this is nothing but a convolution integral, right. We have understood what we have seen earlier. So recall, if you do not remember it now, recall in one of the earlier lectures, very early lectures, even during the classical control phase what we were discussing, yeah, this is the convolution integral, right. So now I am going to just out of nowhere I am going to just not put, I am going to just propose this control, okay. Suppose u of tau or u of t rather is equal to g1 times the impulse plus g2 times the derivative of the impulse, which is the doublet, plus g3 times the double derivative of the impulse, plus so on till gn times the n minus 1th derivative of the impulse. Now of course those of you who are very mathematically inclined will find this a little troublesome, right, because you know, this impulse, as I said earlier, I might have said earlier, is not really a function, it is a distribution, yeah. So it is something that does not take values from the real number, set of real numbers, and cooks up another real number, right. That is not how an impulse is defined, it is more than that, it basically takes a function. So an impulse is defined by what it does to a function. So what is the definition of the impulse? If you see, you take this impulse and you take its convolution with a function, yeah, what does it do then? So if you take this impulse and you take its convolution with a function, yeah, that is how it is defined. So that is basically going to be delta of t minus tau f tau d tau, yeah. So that is going to give you this ft. So in other words, yeah, so this is 0 to t, let us say, Now notice that in this case we nowhere do we actually use the fact that this delta is some mapping. Although we say this is delta of t, we do not really understand it in the sense that you pick some value of t, some real value of t, and you get some function value at the output, right. That is not how it is defined, rather this is the way it is defined. So by the same token you see the doublet, that is the derivative of this delta, we are not really in a position to tell you in a sophisticated manner how this happens, but you see this is defined as this f dot of t, alright. So likewise we go on in this manner, and then no, do not ask me why this is true or how this is true, because that is going to be well beyond the scope of what we are doing here. So this is going to be likewise, yeah. So you have to take a leap of faith with me here unfortunately, not too often that we have done this in this course, but at this point I will ask you to sort of go with me on this, okay, because this is not something that you take the conventional derivative of with respect to time, yeah, and things like that. So this requires a little bit of more sophistication, which you will have to excuse me if I do not indulge in at the moment, right. So now notice that with this and with this kind of a proposed control law, what do we end up with? So let us go back, then we have this x of t2 minus x of t1 given by, after all what was this function, yeah, this is, as I said, this is a convolution of what, yeah, convolution of this. So instead of saying that this is like a single function, this is a vectored function, no, yeah, because see this b is a vector, this exponential matrix exponential is a n by n matrix, so this overall thing then belongs to Rn, yeah. So if I am taking the convolution of this, yeah, with delta, with the delta dot, with the delta double dot, so on with delta n minus 1th dot, so every such convolution I take, if I take the convolution for example with delta, I will get back just g1 times the function. If I take the convolution with delta dot, I will get back g2 times the derivative of this function. If I take the convolution with delta double dot, yeah, the second derivative, whatever that might mean, it will be like g3 times the second derivative of this fellow, this function here. So what are the derivatives of this function? Well, it is a matrix. So when you take derivative on the right hand side with respect to this t, yeah, what you will essentially end up getting is that a times e to the power at, yeah, and we will evaluate that at t is equal to t2, because after all this is what our running variable is, right. So then now you notice what I can write that as is this, yeah. So what I am going to write, okay, I am going to get rid of the integral now. So I hope you followed the step that we are invoking here. We are saying that this entire thing is after all, a convolution, and the function that we are passing through the with the impulse and its derivatives. So impulse and its derivatives are contained here, yeah. This is where the impulse and its derivatives. So this is something that I have just proposed out of the blue, yeah. So of course I cheated, I know how this works, that is why I proposed it, right. In other words, like this is not magic. So I know that I want to go from one state to another in almost 0 time. So there is of course some sort of a jump discontinuity in the state vector, right. So if there is a jump discontinuity in the state vector, I better have impulses in the input, because those impulses in the input will after integration lead to a jump, right. So that is how I sort of intuitively felt that this might work, and as it turns out it will. So what do I get then? So this will then be well b times, so we have g1 times b times e to the at2, e to the at2, yeah, plus g2 times a b times e to the a t2, plus likewise till we have gn a to the n minus 1 b times e to the a t2, yeah. I hope I am not making a mistake, let me just check. Okay, sorry, this order of multiplication is clearly off, my bad, that is really nasty, yeah, sorry about that. So the b should always come at the last, right, yeah, of course. So e to the a t2 b, this is a e to the a t2 b, similarly this is a to the n minus 1 e a t2 b, right, yeah. Now notice that this e to the at2 is after all nothing but a matrix exponential, and we know that a matrix exponential is always going to be non-singular. So if a matrix exponential is going to be non-singular, there is no way you are going to be able to combine the columns of e to the at2 and get 0. So therefore e to the at2 times b is a non-zero vector, yeah, unless b is 0, and b we know of course is not 0. If b is 0, then there is no way you are going to apply any control, right. So b is not 0, e to the power at2 is an invertible matrix, so therefore e to the power at2, yeah, times this b is going to be a non-zero vector, yeah, but we can actually do more, yeah. So what are we going to do now? You see, we can say that this and this a and e to the at2, they actually sort of, you know, commute, right. So a and e to the power at2, they commute, right, because we know that a commutes with any exponential thereof. So therefore I can write this as x at t2 minus x at t1 is equal to, hang on, what is this, yeah, summation, yeah, so let me just write it explicitly. So this is g1, and I am going to pull this e to the at2 out, yeah, so I am going to just pull this e to the at2 out, because after all this is scalars, no, yeah. So I just flipped the order. Remember what I did was just I flipped this order, yeah, these commute, yeah, because after all this e to the at2 is a series of I plus at plus a squared t squared by factorial 2, so it is only a squared multiplied with a cubed multiplied with a, so they commute, yeah. Please check that if you are not convinced. It's a very simple exercise, but you should check, you shouldn't just believe me. So then what I have here is g1, what was it, g1b, right. So g1b plus g2ab plus dot 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 till I have gn a to the n minus 1 b, but this now I can write as e to the at2 times, look at this now, b ab dot 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 till a to the n minus 1 b, right, and then I write this as g1 g2 till gn, and this I know, as I said, is an invertible matrix. So I then have, suppose I want to go in almost no time from this to this, yeah, this is where I want to go, then this is a vector that I know, so this is a vector, and I pre-multiplied with e to the minus at2, this inverse exists because matrix exponential, in fact we have shown that the state transition matrix is itself an invertible matrix. So this is completely known to us, we know, right, so this is known. Then what do I have here? This is after all nothing but that old friend of ours, that controllability matrix. So this is controllability matrix, and this is just g1 g2 dot 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 till gn. So this is my only unknown. So if I want to go from one point in the state space to another in almost no time, I have at least shown you that using this hypothetical, this sort of theoretical artifice, that is these impulses, I can put certain weights on these impulses and get my states to go from one point to the other, subject to the fact that, or subject to the condition that this controllability matrix is invertible. That is all that I need, and then my solution is going to be the C inverse e to the minus at2 times whatever that is. Let me just write the complete thing here, yeah, xt1 is equal to g1 dot 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 till gn. That is how I can determine these unknowns, yeah, and then I can apply that input in theory, of course, that we are allowing this impulses and their derivatives. So now you can imagine that, well, the more the time you give me, the more I can relax this. I do not need an impulse now, I need functions which are not as high energy as these impulses, right. So that is essentially what the point of this exercise is, right. So we have actually now shown you that this solution exists and controllability allows you to do this. So although I have not given you a complete characterization of the solution in terms of the controllability Gramian, which as I said is beyond the scope of the syllabus, but at least hopefully this appears convincing to you that indeed what we have done here makes a lot of sense, and therefore this controllability is not just a necessary but a sufficient condition, right, for me to go from one state to another in any given time duration that is allowed to me, right. So this tells you that we can do this, and controllability is therefore a very key property. So now that we have come this far, let us check this test, or let us test this condition that we had said a while back, that the phase variable canonical form is always controllable. Okay. So why is that so? Let me put the phase variable canonical form in this fashion. So 0 1 0 0 0 0 0 1 0 0 0, likewise till you get the last but one row 0 0 0, and you get a 1 here, yeah, likewise, and the final entry is the final row, you have these, the coefficients of the characteristic polynomial. Yeah. So this is how you get, and this is how your A matrix looks, and your B matrix looks typically like this. Yeah, this is going to be how your B matrix, yeah, this is going to be how your B matrix looks, right. So now notice what is B, AB, A squared B, so on till A to the n minus 1 B going to look like. This is going to look like, the first column is obviously going to be this B itself, which is this. Now the second time you multiply A with B, pre-multiply A with, what is this going to do? This is going to pick out this last column, isn't it? It's going to pick out this last column. So you have this 0 0 0 0 till 1 and something sitting here, right. What about A squared B? So this is basically this. Let me use the next color. What about A squared B? So A squared B is like when this fellow is pre-multiplied, when this green fellow is pre-multiplied by A. So you look at this A and pre-multiply this green vector, this vector with A. What do you get? It basically says you take 1 times the last but one column plus the start times the last column, but this last but one column has what structure? It has 0 0 0 and a 1 sitting here and a 0 here and some star here, which I do not care about. But the big point here is that note, you can proceed likewise and you get to a point where this is like an anti-diagonal matrix where all the ones are sitting along its anti-diagonal. Oh sorry, did I say anti-diagonal? Actually it's not anti-diagonal because they are clearly non-diagonal entries which are non-zero. So it should be anti-lower triangular perhaps, to be precise. Yeah. Yeah. All the ones are sitting along its anti-diagonal. Yeah. So this is my controllability matrix. So my claim is that this is going to be a invertible matrix, an invertible matrix or a full rank matrix. But how is it, how can I justify this? How can I say that it is indeed going to be like so? Now notice, hang on, where was I? Yeah, so if you now want to find out the determinant of this C, what can I do? I can always expand by the first row and the second row and so on. So if I expand by the first row, I will be eliminating the first row and the last column while expanding by this, yeah, and then what I have is this. So again I will have this 1 here. So let me see, what is the determinant of this controllability matrix? So you see, it's not very difficult, yeah, it may not be very straightforward like an identity matrix or whatever, but you see if you expand it using this Laplace's expansion rule for determinants by row wise, so then the first row has only one non-zero element, so you expand it by this, and then of course when you expand it by this, the minor that you considered is this, sans this first row and the last column, and so then you take this, and again in that one it has the same structure, it has a 1 sitting over here. So likewise if you expand, you will see that after a certain number of flip-flops, it will be either +1 or a -1, and again like in the observer canonical form that we have seen, right, where the observability matrix was always full rank and its determinant, because it is a square matrix, was non-zero and in fact independent of the parameters of the matrix for that matter. Here also you see it is either +1 or -1 depending on the size of this matrix really, but it is independent of any other parameter. So that adage that goes that the phase variable canonical form is always controllable, yeah, that you can now verify. So what have we seen? One way we have of seeing that is, of course, as we have defined through from the definition itself ab initio, we have shown you that you can always cook up. We have actually explicitly cooked up this explicit input for you, which takes you from one point on the state space to another in almost infinite time, right, in almost no time. So again I ask you to believe me on that, that if you give me some finite time, which is basically a relaxation of the condition, you will still have an input. To cook up that input in a closed form will involve, again as I said, some Wronskian, some Gramians that we define, which is beyond the scope of this course really. But I hope that you are at least convinced that there does exist an input which takes you from one point on state space to another in any given amount of time, which is what is consistent with the definition of controllability. And now you see that it passes this test of controllability as well, which is to say that this controllability matrix has full row rank, in which case here it will have full column rank as well because it is a square matrix. By virtue of that, it means that the determinant must be non-zero, and here we have shown you not just is it non-zero, it is actually independent of any entries of the A matrix, and in fact it is just plus or minus 1, right. So that is what goes behind this, and in fact there is a good reason why this is also called therefore the controller canonical form. So in a few lectures from now, when we discuss the controller design aspect, you will see that this form is particularly handy in designing a controller. It is in fact very explicitly seen what the controller parameters would be. Of course what that controller will look like is another matter, we will need to do some groundwork before we describe that, but nonetheless this form lends itself easily to the design of a controller which allows you to place apparently the eigenvalues of this A matrix anywhere. Anyway, I am getting ahead of myself. So that is the reason why it is called a controller canonical form, alright. One more interesting aspect that I would want to talk about this particular representation before I go into something. Notice that if you have a C matrix that is given by 1 0 0 0 like this, yeah, then with this phase variable canonical form you see the observability matrix turns out to be identity. I leave that to you as an exercise to check, okay. Check that with, if the C matrix were now of this structure 1 0 0 0 0 like this, yeah, then with this phase variable canonical form representation it is actually very easy to check. This actually filters out the first row of a matrix. So the first row will be C, then will be CA, likewise till CA to the power n minus 1. So you check that the observability matrix, so this is, remember, not a typical phase variable canonical form representation, a very special case of phase variable canonical form representation in fact, yeah, where you have only the first entry of C as non-zero and the rest are all 0, and then you will see that it is also fully observable. Later on when we shall talk about something called joint observability and controllability and what it means, what the notion of so called minimal representation is, we will see that it entails no pole 0 cancellation, and then this will begin to make even more sense, because then you will notice that having a C matrix like this, again I leave that to you as an exercise. So there are two exercises, one marked in black to check that indeed the observability matrix is a full rank for this sort of a C matrix in the phase variable canonical form. So as I said, remember, phase variable canonical form imposes no particular structure on the C matrix, it is that just that I am imposing this sort of a C matrix. Apart from being in the phase variable canonical form, I am saying that this is the C matrix, in that case it will be fully observable, yeah. And the second exercise is, of course it will come a little later when we have discussed this minimality and joint controllability observability, you will see that with this sort of a C matrix there are actually no zeros in this system, that you can see right away even now. So now if I tell you that basically a system where there is no pole 0 cancellation is fully controllable and observable, look, if there is no finite 0 at all, then the question of cancellation of pole 0 does not arise, so naturally it is going to be fully controllable and observable. Of course I am talking about something that might appear a little advanced at this moment, and you might be wondering, might be scratching your head as to what it means. Hang on, wait for a while till we discuss what joint controllability and observability is and what the notion of pole 0 cancellation and minimality is, yeah, and then you put 2 and 2 together and then revisit this, yeah, and I want you to get this insight clear as to why if you choose a particular C matrix like this in the phase variable canonical form, then you will always have both controllability and observability. However, in general for an arbitrary C matrix, it is not easy to see what the rank of the observability matrix will be, yeah, because then it will not depend just on it will not just be an identity matrix, it will depend on the parameters of this A matrix as well, right. So now we are going to look at some analogous things like we did for the observability bit, right. So we are going to see that whether if I start from a controllable realization and if I go through a similarity transformation, if all I am going to always get is also a controllable realization, right. So that is the question that we are going to be interested in now, okay. So let us see why, if it is true, and if so then why it is true, okay. So suppose you have this C matrix, again just like the observability matrix was a function of AC, this is going to be a function of AB is equal to B till A to the n minus 1 B is invertible, yeah. Now consider T inverse AT and T inverse B, the controllability matrix for this realization. What is it going to be? Well, it is going to be T inverse B times, look at any typical fellow here, A to the power K B, where K is less than or equal to n minus 1 and greater than or equal to 0. In fact, it is greater than 0 you can take, because we already seen the case of K is equal to 0. So let this be greater than 0, yeah. For look at this, okay. So now notice that this is going to be, or rather I should say look at T inverse AT to the power K and T inverse B, yeah. Look at the transform side, yeah. So that will be equal to T inverse AT, T inverse AT, yeah. Like this I take T inverse AT, like this I take K times, and then I take T inverse B. So what am I left with? You see, in between these fellows they pulverize each other. So what I am finally going to be left with, and even this fellow pulverizes this. So what I am going to be just left with is T inverse A to the K B, right. So therefore each typical term here is going to look like T inverse A to the K B till I end up with T inverse A to the n minus 1 B. But what is that? That is going to be nothing but T inverse the controllability in terms of AB, yeah, right. So now the question is this fellow invertible? Because if this fellow is, so the question is this invertible? Because if this is invertible, then it means that starting from a controllable realization you go to another realization through similarity transformation, and that second realization is also going to be controllable. So how can we show that? Again, these are, I can even give them as exercises in fact, but let me go ahead and do it. So consider CAB. So this CAB inverse T. Now this exists, yeah, this exists because the original realization in terms of AB is controllable, right. So now let me draw a line here, this C inverse in terms of AB times T times C in terms of T inverse AT and T inverse B is going to be equal to what? Notice that this is in turn equal to this, so I can substitute this here. So this is going to be C inverse AB times T times T inverse times C AB. So again this T and this T inverse are going to pulverize each other, so you are going to be left with C inverse AB times C AB, which is nothing but equal to identity. So therefore this is, it turns out explicitly I have constructed an inverse. So this is an inverse for the controllability in terms of T inverse AT and T inverse B. So therefore it is invertible because I have cooked up explicitly an inverse. Now there is no argument, end of the story. Yeah, I have already cooked up an inverse, so it is going to be invertible. There is no two ways to it. It cannot help but be invertible, correct. So now if that is the case, then I have shown you that in going from one controllable realization through a similarity transformation to another, the second realization will also have to be controllable. Now we ask the dual question again, right. So we ask the dual question. The dual question is that if I realize a system in one controllable form and you realize the same system starting from a transfer function or ODE in another controllable form, so this is CTRB, this is controllable, and this is also CTRB, this is also controllable, yeah. So this is SSR1, this is SSR2. So the question is, does there exist a similarity transformation like it did for the observable case? And by now you might have guessed the answer. I mean, yeah, no prizes for guessing because it will follow exactly the similar pattern, the proof or the claim, yeah. So the claim is that there does exist such a similarity transformation which takes you from one side to the other, yeah. So if two of us realize a particular transfer function in two different controllable forms, yeah, then there will exist a similarity transformation going from one to the other. How are we going to prove this? So now consider C inverse A C. So again let C inverse is equal to say Q1 transpose Q2 transpose like this till Qn transpose, yeah. So these are the columns of this. Okay, yeah, all right. So now what we know is that, well, Q1 transpose Q2 transpose dot 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 till Qn transpose times B AB dot 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 till A to the n minus 1 B is going to be identity. So from this I can deduce that Q1 transpose B, which is just a scalar, is going to be 1, and Q1 transpose A to the power anything other than 0 times B is going to be 0 because these are all zeros, right. That is going to give me the first row. So therefore, okay, let me use this space up here. So therefore Qi transpose times A to the I minus 1 times B is equal to 1, and Qi transpose A to the K B is equal to 0 otherwise. You can look at it that it always holds, right. Unless K is equal to I minus 1, Qi transpose A to the power K B is always going to be 0, yeah, because of the definition, right, that this is the inverse of the controllability matrix, yeah, and because this is controllable, so the controllability inverse matrix always exists, and if it exists then this is the rule that it must follow. So now what I am going to do is I am just going to push in an A here and see what happens. So I am going to now push in Q1 transpose Q2 transpose dot 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 till Qn transpose A, and then B AB dot 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 till A to the n minus 1 B, and let me push this A inside here. So that is going to be equal to, so this is, remember, this is the controllability inverse, this is the controllability, yeah. So then I am going to get this Q1 transpose dot 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 till Qn transpose times AB A squared B dot 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 till A to the n B, alright. Now I am going to revert to this rule that I have just seen because of this inverse. So what can I see then? You see this Q1 transpose AB, yeah, what is it going to give me? It's going to give me 0. So apparently everything other than apart from till the last term, this a to the power n minus 1 b sitting here, this last but one column is going to give me 0. But what about the last term? Again by Cayley-Hamilton theorem, this a to the power n is going to be minus alpha 0 I minus alpha 1 a minus alpha 2 a squared minus dot 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 till minus alpha n minus 1 a to the n minus 1. Yeah. So now if I am multiplying this Q1 transpose, pre-multiplying with this, you see Q1 transpose this time, so a to the power n b is going to be this times b, this times b, this times b, and this times b. So now notice that if I pre-multiply every element here, this is just a sum, no? So if I pre-multiply every element here with a Q1 transpose, I am going to get Q1 transpose b. Yeah. So only minus alpha 0 is going to be picked out from here. The moment I pre-multiply Q1 transpose with AB, it's going to just be 0, right? So I'm just going to get this as 0 0 0 0 0 till minus alpha 0. Similarly, when I do with Q2 transpose, when I operate with Q2 transpose, I'm going to get the first element here, Q2 transpose AB. Note that Q2 transpose AB must be equal to 1. Yeah, so I'm going to get this Q2 transpose AB as 1 here, then I'm going to get a 0 0 0 0 till again the last fellow it is going to pick out minus alpha 1. So the last fellow you can keep checking, it's going to pick out till minus alpha n minus 1. And what about this pattern? This pattern continues like this, likewise. Yeah. So this is irrespective of anything, right? I have not assumed any particular structure of A. I have only assumed that A is controllable, and if A is controllable and you hit it from the left side, if you hit the A matrix from the left side with C inverse and you hit the A matrix subsequently from the right hand side with the controllability matrix C, this is what you are going to get. So therefore, just like I did for the observability case, now I get that C1 inverse A1 C1 is equal to C2 inverse A2 C2, right? And therefore I have that A1 is equal to C1 times C2 inverse times A2 times C2 times C1 inverse. Yeah, just hitting on the right hand side by C1 inverse and hitting on the left hand side with C1 on both sides, this is what I get. So now suppose I define this, or rather this as my T, then you see that this is T inverse clearly. You multiply them together and you see that C1 inverse, C1 C2 inverse, and then C2 C1 inverse, you are going to get identity, right? So if you define one of them as T, then the other is T inverse. So this is a similarity transformation. Again you might say, what is the guarantee that the same similarity transformation works for B and C? So I urge you to check, just like we did maybe in the last lecture or so, with B. So if you take now this, where was I? Yeah. So now if you take, for example, C inverse B, what does that give you? It gives you Q1 transpose dot 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 till Qn transpose B, right? So what is Q1 transpose B? Excuse me. What is Q1 transpose B? You will see that Q1 transpose B, yeah, that means I is equal to 1, yeah, and so therefore Q1 transpose B is the only fellow that is unity, right? So therefore this is going to be of the form 1 0 0 0 0, yeah. So therefore I have that well B1, and if I hit it with the C inverse, C1 inverse, then what I get is the same as if I hit B2 with C2 inverse. Yeah, so C1 is the controllability in terms of A1 B1, C2 is the controllability in terms of A2 B2, where A1 B1 and A2 B2 are both controllable realizations of the same transfer function. So then what do I get? Just like I got here A1 in terms of A2 as a similarity transformation, can I not get B1 is equal to C1 C2 inverse B2? But by my definition, notice that the C1 C2 inverse is T inverse, yeah, so that is equal to T inverse B2. So again we are faced with the same question as before, that okay, you got your A and B, but controllability deals with A and B, so maybe that's why you got the A and B. What about the fact that the C does not affect the controllability? Will we get a unique C? So maybe you have matched in the A and B, but what about the C bit? Do they match in the C? So again I urge you to check that if you have two realizations where you have C and C tilde, so you have A, B and C as one realization, and A, B and C tilde as another realization, and both controllable, yeah. Then what do you get? You have to have that C times Si minus A inverse B is equal to C tilde times Si minus A inverse B, or in other words you need to have C e to the power At B is equal to C tilde e to the power At B, right. But remember, again this time I am not going to go the long route. I have already seen that when this is true, then this also means I have shown you this already, right, by taking differentiations of the impulse response at t is equal to 0, maybe 2-3 lectures back. So then this means that C A to the power K B is equal to C tilde A to the power K B for all K greater than or equal to 0, yeah. This we have already proved. No, we have already proved this. So remember, in the observability case I proved it in a different way, in the controllability case a slightly different way, because I am now going to use this result, which also I had proved some classes back if you look back on the lectures. So then that tells me that, look, if I can construct this C minus C tilde, and then I have this A to the power KB is equal to 0, yeah, for all K, right, for all positive or non-negative K, for all K is equal to 0, 1, 2 like this, yeah, it goes till infinity. Now therefore I can stack this up and write this as B, AB, yeah, A to the power n minus, at least till n minus 1 this holds true. Then if it holds for all T, then it holds all K, then it holds for this also. So then C minus C tilde, sorry, this is not that controllability C, huh? So I should not write the curly C here. So this is the C, the output C, yeah. So C minus C tilde is equal to 0, but then again look, this is going to be a full rank matrix, this is going to be an invertible matrix, so every one of its rows is linearly independent, as are every one of its columns. It is going to have full row rank, right. So if it has full row rank, then all its rows are linearly independent, but here this is a vector, let us say some V bar, which is claiming, so V bar transpose, because C is, remember, a row vector, so C minus C tilde is also a row vector, so which can be written as V bar, where V bar of course belongs to Rn, yeah. But this means that there is some combination of these columns of this matrix, or of these rows of this matrix, which leads to 0, but that can only imply that V bar is equal to 0, because if there is a non-trivial, non-zero combination of the rows that gives you 0, then it can only mean that the overall stuff, this overall thing, yeah, is linearly dependent, therefore this controllability will be violated. But since clearly that is a contradiction, so therefore we must have V bar is equal to 0, but that also implies that C must be equal to C bar, C tilde, right. So therefore we come to the conclusion that, just like in the observable case, we find that if you and I have realized a system, a transfer function in a realization that is observable, may not be that our A and B matrices and C matrices and D matrices they match, yeah, D matrix has to match of course, but may not be that our A, B, C matrices match, right. But if both of us have maintained this property, this sanctity, that they are both controllable, then at least, yeah, we can go from one to the other uniquely, yeah, this similarity transformation, yeah, we can go from one to the other, yeah. That is precisely what this tells us, yeah. You can take this controllability or its scaled version of this controllability matrix thereof, and you will go from one to the other form, okay. So that sort of completes the picture. Now we have two bags, so we have this transfer function or the ODE, yeah, and now here you have one bag containing all realizations that are observable and one bag containing all realizations that are controllable. And you see that between every two realizations in this first bag, which is bag of all observable realizations, you can go from one to the other. You can go both ways from one to the other through similarity transformation. And again, if there are any two realizations here in this bag, you can go from one to the other, any one of them, right. Now the problem is that we still do not know whether a connection between these two exists, right. So it turns out, a bit of logic will tell you that if there exists at least some realization, yeah, which is both controllable and observable, right, then every other realization of that same size, yeah, is going to be controllable and observable, no. Remember, if these two sets have something in common, yeah, if these two sets have something that is overlapping, so if this bulges out into this and this set bulges out into this, yeah, if these two sets have something in common, yeah, some element sitting here that is both controllable and observable, then from this I can go to any member of this set and I can go to any member of this set, and therefore this is like acting like a bridge. So I can go to any member of this set from this set through this. So I know the similarity transformation that takes me from here to here, I know the transformation that takes me from here to here. So just by composing those two similarity transformations, I can go from here to here. So it turns out that if there exists one realization which is both controllable and observable, yeah, then I can go from any other realization of that same size, yeah. This is called the minimal realization. So we will see that this motivates us to study further this property called joint observability and controllability. So now that we have seen individually the properties of controllability and observability, in the next lecture we shall talk about this property called joint observability and controllability, which will very naturally then lead us to this notion of minimality, okay. So till then, take care, thank you.